Hello and welcome to this clip on isotopes and relative atomic mass. We'll cover the basic structure of the atom from GCSE, including specific details of the main subatomic particles, the neutron, the proton and the electron. We'll have a look at how we use atomic number and mass number, what an isotope is, and how we define and calculate relative atomic mass. And then we'll look at some examples of examination questions on this topic. So at GCSE you would have learnt that an atom contains a nucleus, and the nucleus has positive protons and neutral neutrons. It also contains electrons sitting in or occupying shells around the nucleus. And one of the first things you come across in exam questions at A level is being able to work out the charge and the mass of a proton and a neutron, and applying that idea to a specific named atom. So if we were to think of the mass in terms of relative mass, in other words, comparing the proton and the neutron and the electron to each other, the relative mass of an electron is around 1 over 1,800. So what we really do is we consider the mass of the electron to be negligible. So we consider the mass of the electron to be negligible and don't really use it in atomic mass calculations. So for each element in the periodic table, you'll have a box with the symbol of the element inside the box. You'll have two numbers. One will be the mass number, one will be the atomic number. The mass number is always the larger of the two numbers. So whichever periodic table you're looking at, the larger of the two numbers is always going to be the mass number, because it accounts for the combined mass of the protons and the neutrons. If you're trying to work out how many neutrons an atom has, all you have to do is subtract the proton number from the mass number, or the atomic number from the mass number. So in a neutral atom, the number of positively charged protons will be the same as the number of negatively charged electrons. So if you wanted to work out the number of electrons, all you have to do is look at the proton number in the box in the periodic table. If on the other hand you're looking at an ion, which is a charged atom, the charge will indicate if there are more protons than electrons, in which case it will be positively charged, or more electrons than protons, in which case it will be negatively charged. If this is the case, you have to try and use your judgment. Let's say it's +2, the ion, that means it's got 2 more protons than electrons. If it was -3 in its charge, it would have 3 more electrons than protons. So let's see if you can apply this to some examples. I've given 3 common ones, and I'd like you just to pause the video, jot these down on a piece of paper and see if you can write out the number of protons, the number of neutrons and the number of electrons for each species. So the first one is 17 protons, because the proton number is 17, you can see it clearly. And also 18 neutrons, which is 35 minus 17. And because protons equal electrons in a neutral atom, then you're going to have 17 electrons. So in magnesium 2+, you'd have 12 protons and 12 neutrons as you'd expect, but only 10 electrons. So how come? So the 2+ charge means 2 electrons have been lost. So your expected number of electrons, which would be 12, to match the number of protons, has to have 2 taken away. So that gives us 10. And in the third example, 2 electrons have been gained this time, so 8 plus 2 equals 10. The 2 minus shows that there's 2 electrons gained, 2 negative charges have been gained, remembering that electrons are negatively charged. So do watch out for ions in exam questions. They're liable to throw that at you to see if you're on your toes here. So let's have a look at how this is applied to the periodic table. I'm going to have a look at the periodic table copy that you've got for your specification. So if you look at this copy of your periodic table, you'll see that the mass number is actually replaced with the relative atomic mass, which accounts for the presence of isotopes. And you'll see as well that many of the relative atomic masses have decimals And this will come from calculating the relative atomic mass. And you may have also noticed that the atomic number and the relative atomic mass seem to be placed at the opposite sides of each of the boxes. It doesn't really matter if the atomic number is at the top or the bottom, because the atomic number is always the smaller number out of the two. If you just remember, the smaller number is the atomic number, the bigger number is the relative atomic mass. So for an isotope of an element, the smaller number equals the protons, the bigger number equals protons and neutrons. So what we're going to do now is try and explain why the relative atomic mass has decimal points, and also explain what an isotope actually is. So it's impossible to weigh atoms directly. So what we do is we have to use some kind of comparative way of measuring their mass. That's why we call it the relative atomic mass and just not the atomic mass. So we need to find an atom that we can compare everything else to. Although at first glance something with an atomic mass of 1, such as hydrogen, might be obvious, we actually use the isotope carbon-12, because the weighted mean mass of all its isotopes is much closer to 12 exactly. So we therefore say that the relative atomic mass is the weighted mean mass of an atom of an element compared to 1/12 of the mass of an atom of carbon-12. So we use 1/12 because it allows us to divide the exact accurate number of 12 by 12 to give us 1 to compare things with. So because carbon has a relative atomic mass of very, very, very close to 12 exactly compared to hydrogen, we use this comparison. So sometimes we get different versions of an element, and these different versions have different numbers of neutrons in the nucleus. But the number of protons will be the same, and as such the number of electrons will be the same. So the only thing that will be different between them is the mass, but the chemical properties will be identical. And that's because they only depend on protons and electrons, not neutrons. So that means that isotopes get their own relative mass as well, and that's defined as the mass of an atom of an isotope compared to 1/12 the mass of an atom of carbon-12. So we calculate relative atomic mass by taking the total of the mass times percentage abundance. So you'll have a mass for each isotope and a percentage abundance for each isotope. You multiply them by each other and then you divide that by the total of all the abundances. Generally, the data you're given will have all the abundances adding up to 100. We get hold of this information by using a mass spectrometer. So the next slide will briefly explain what we get from a mass spectrometer to enable us to do this calculation. So if you look for chlorine, for example, on the periodic table, you'll see that it has a relative atomic mass of 35.5. And this is due to the fact that it's got two naturally occurring isotopes, so any sample of chlorine will have 75% of it will be chlorine 35 and 25% will be chlorine 37. So we can't simply take an average of 35 and 37 because the two isotopes are clearly not present in equal proportions. So if we were to pass a sample of chlorine through a mass spectrometer, we get a mass spectrum that looks like this. So the bottom axis is the m over z value. So the m refers to the mass and the z refers to the charge. So the charge comes from the fact that the atoms of the chlorine are ionized in the mass spectrometer. So once they're ionized, they'll then exist as ions of two different masses. Some will be 35.0 and some will be 37.0. So how often each of these different masses are detected is calculated by the mass spectrometer and converted into an abundance. So the printout that you get will be your mass spectrum. So if we perform the calculation that we talked about in the last slide, taking the total of percentage times a mass, or the mz value, then basically that gives us 35.5. And the m over z value that the spectrum gives you
will be equivalent to the mass, because the atoms are ionized in the mass spectrometer into ions of a 1+ charge. So the next thing to do is obviously try this out on some practice questions. So the next slide will show you some typical exam-style A-level questions on this, and we can work through them together. So when you get to the next slide, why not pause it before I take you through the answer and see if you can start to work it out for yourself, and then play when you're ready to see the answer and see if we agree. So the question gives you some information about the element titanium. It tells you that its atomic number is 22, so that allows you to locate it in the periodic table that you'd have, obviously, if you did any tests or exams. And it also gives you some information about its isotopes. And you can see them there. It said that it was analysed using a mass spectrometer, which you can see here. So then it gives you some isotopic information. It gives you the relative isotopic mass for each of the individual isotopes, and also the percentage composition. It's a good idea at this point just to quickly note down, does the percentage composition add up to 100? In this case it does, but it's always a good idea to double check that in every question, because very occasionally they might not give you all the isotopes, they might give you only a couple and expect you to deal with it. So let's say they gave you a couple and they added up to less than 100, then you wouldn't be able to use 100 as your total of all abundances, because you wouldn't be taking into account the other isotope they didn't give you. So thankfully, this question doesn't do that to you. It's a nice straightforward one. So the first thing to do is to explain the term isotopes. So you might want to go to your glossary in your textbook, or perhaps make a flashcard from the glossary at the back of the textbook, and then come back and give this a try. So I put down that it's atoms of the same element with different number of neutrons, with the same number of protons and same number of electrons. Even though it's only 1 mark, please make a note of the fact I've been specific and the fact I've used detail. They really need you to do that at A level. You don't just put down different number of neutrons or same number of protons and hope that the examiner will put the rest together for you. They will not do that. They simply won't give you the mark. So you have to make sure at A level that you're being as detailed and as specific as possible. So let's now bring the page down and look at the next part of the question. Now it says complete the table below for atoms of 2 of the titanium isotopes. It gives you 46 titanium and 47 titanium. To do this, we're going to have to look at the periodic table. Now I'm assuming that at this point we can pause the video and you can get hold of your periodic table, which you should have. If not, it's in the back of your textbook. So pause the clip, get your periodic table, and then we can come back to this. So remembering that the value that's given is the protons plus the neutrons, you can use the proton number of 22, sometimes called the atomic number, and take it away from the mass number to give you the number of neutrons. So because these are isotopes, notice that the protons and the electrons, the numbers stay the same. It's only the number of neutrons that actually changes. So moving the page down again, it says using the information in the first table, calculate the relative atomic mass of this sample of titanium. So this is going to be our calculation we've talked about in the last part of the previous slide. So there's the information again. You might want to pause the video and jot it down. So now I'm assuming you've got that on paper. Let's go down and do the calculation. So I've written the relative atomic mass shorthand, A subscript R, put in brackets Ti, my element, and I've applied the isotopic mass times the relative abundance each time, added them all up, divided by 100, which is the total of all the abundances, and that gives me 47.7, and I've underlined that to bring the examiner's attention to that fact. So the next question says a 50p coin contains nickel alloyed with the metal A. And nickel exists as a mixture of three isotopes, nickel 58, nickel 60 and nickel 62. And again, it's the same sort of idea, isn't it? You've got to look at the periodic table to find out nickel. So you'll need your data for nickel before you can go any further, so pause the video and grab your periodic table. And that gives us the same kind of situation as before, except this time obviously the numbers are different because we're talking about a different element. But what's similar to the one we looked at before is that it's only the neutrons that change from one isotope to another. The protons and the electrons always stay the same. So I'm accenting when I say that to you because it's really easy to forget. But once you've drilled yourself on it and practiced it a few times, it's really straightforward and it's easy marks. You can see just for doing that, 3 marks straight there. So now let's bring the page down a bit and let's look at the final question. Okay, so it's a similar idea again. So again, this time, go to your periodic table and find magnesium. And hopefully you came up with those numbers. Now in this next one, it asks you to calculate the relative atomic mass of this sample of magnesium. But it wants you to do it to 4 significant figures. That's a direct instruction. And you'll see that there's actually 2 marks. So 1 mark will be for getting the right calculator answer, and the other mark will be for converting it to the correct number of significant figures. Please always remember to do this. It's the number one thing that people forget to do, and they always lose a mark for doing it. If you're told to do it to a certain number of significant figures, do it to that number that's quoted. So if it was to 2 significant figures, or 4 decimal places, or 3 significant figures, you have to stick to that mathematical convention. So you can see that my calculator value is 24.3269, but that's actually 6 significant figures, isn't it? To bring it down to 4 significant figures, you have to round it 32. That makes it 24.33. So don't forget to do that. So let's go to the final part of the question. And it says to define the term relative atomic mass. And like we said earlier, it's the weighted mean mass of an atom compared to 1/12 of the mass of an atom of carbon-12. So now we can go on to the answers. So I think all that was pretty much what we did. This mark scheme's from a slightly earlier specification to yours. In the one that you're doing, you need to say same protons and different number of neutrons, and therefore different mass as a result. So going down to the nickel one, each column has to be correct because it shows that you understand that the protons and electron numbers don't change, but the neutron numbers do. So what ECF means is error carried forward. Don't rely on it in mark schemes. It varies from year to year. Sometimes examiners are generous and allow you to make a mistake early on and then do the right thing with that mistake later and not lose the second mark. But in other years, they're quite fussy and don't allow you to do it. So try to make sure you're getting your answers right first. That would be the obvious advice. So on this one, it was the same. Again, first line correct for magnesium 24 and the second line correct for magnesium 25. This time it's marked by row. Either way, it makes sure that you understand that the proton numbers remain the same, but the neutron numbers change, and that the electron numbers also remain the same. So moving the page down, we got the calculator value eventually. By doing this calculation, we obviously bracketed our work. I would suggest perhaps bracketing it just like that. It makes it a bit easier to manage on the old calculator. And there were some possibilities for getting 2 marks or 1 mark, for example, if you get one part of it wrong. Now on the definition, you have to talk about mass, you have to talk about an atom. If you miss out mass or atom, you don't make it. 1/12 is really important and related to carbon-12. So there's a few possible other ways you could do it. Don't worry too much about 1 mole. You can see down the bottom we haven't done moles yet. If you're watching this video early on in your time at A-level chemistry, if you're watching it as a review, then clearly you'll have come across the idea of a mole. But you may not have come across the idea of a mole if you're watching this right at the start of the course. So don't worry about that. Bear in mind that these mark schemes are for exams that will be taken at the end of the course. Okay, so hopefully this was a reasonably useful introduction to the idea of relative atomic mass and isotopes. If you have any queries, come to one of us at Subject Extension at college, or ask your teacher in class. But in the meantime, thanks for your time and see you soon.